So in this video, we'll talk about the integral test and the p-test, and you are recommended to have watched the video about the improper integrals. And because in this video is about integration, as you can see from the name, integral test. And please take a look at the conditions I put out here. I require that all the terms are positive for the infinite series under consideration. It means that if you look at an infinite series, if you see some terms which are negative, there's a chance that it may not be appropriate to apply the integral test. And in that case, if all the terms are positive, I'm saying that essentially you can let a function f of n be a n. And if you consider this function as a function with a continuous variable x, if it is a nicely behaved function, and I want to be informal here. My explanation is a little bit loose. It's not formal, but nicely behaved function actually means it is actually something like continuous function where you can integrate. Because as you can see, we have to do some integrations here. And in the case that f of x is a nicely behaved functions, I claim that the understanding about the infinite series to see whether it is convergent or not, you see, is actually equivalent to the problem of determining whether this improper integral is convergent or not. So the answer should be the same. That's what I said. So it means that if you are good at doing this kind of improper integral and you can determine whether something is convergent or divergent depending on this function f of x, you can easily tell me the answer for the original infinite series. And let's look at the problem now. So please look at the current problem. It is the famous harmonic series. So you see, if you're not familiar with the notation, basically you're adding infinitely many terms, starting with the fact that the first term is based on n replaced by 1, right? So basically you have a long infinite series like this. We would like to determine whether it is a convergent series or not. And the fact is that sometimes, as a good habit, you can try to review some previous tests you have learned. The first method we learned in this topic is about the geometric series. So you can think about it. Is it geometric? If it is yes, I don't think we need to learn any new method to solve this problem. The answer is quite obvious. It is no. You can check there's no fixed ratio that you can use as a multiplicative ratio to multiply to the current term to get to the next term. The ratio is not fixed. And the second test we learned was based on the previous video. It is the M-term divergence test. This test is easy to perform because you just have to take the limit of the individual term inside the infinite series. And I think this one is quite easy. Conceptually, it's the same as 1 over infinity, which is 0, right? And if you recall, whenever the limit is 0, we say there's no conclusion about the answer. No conclusion means our test fails because we don't know whether it is convergent or divergent, right? And let's come to our modern method in this video, which is about the integral test. An integral test means you have to let f of n be 1 over n. And first of all, please look at the terms. These are all positive, right? All of these are positive. That's the first step. It is fine. That's the basic requirement of applying the integral test. And you can look at the corresponding function based on the term 1 over n, which is 1 over x. So this function is nicely behaved. You can differentiate it, you can integrate it, except the point x 0. But we don't have to look at the point x equals 0 because by the integral test, you have to carry out this integration. And I trust that you're able to do this integration, so I just write down the steps here. So please look at the steps that I've done based on the improper integral here. And the antiderivative of 1 over x is ln x, right? And essentially, if you take it from 1 to infinity, it's really formally the same as the limit b goes to infinity for the upper limit b. But anyway, if you try to drop the formality, it's still okay. When the fact is that when you look at this one, you're replacing something like the top part, this b is going to infinity for ln of b. The second term is ln 1. Ln of 1 is just 0, so we can drop that. The fact is that the ln of b when b goes to infinity conceptually is the same as ln of infinity. And ln of infinity, because of the fact that the function ln x keeps increasing without any bound, which when x goes to infinity, we should know that ln x still goes to infinity, although the rate of increase is very slow for the ln function. But anyway, the fact is that it still goes to infinity, which means it is a divergent integral. It means we successfully solved this problem based on the integral test. So our original problem is also divergent. Let's look at one more problem. Let's look at the current infinite series, and once again, you cannot use the previous method you learned to solve this problem because it is not geometric first. And I think the n-term test is not working because when you take the limit of the term inside, which is 1 n squared, it is conceptually the same as 1 over infinity, which is 0. And whenever the limit of the individual term is 0, this one has no conclusion for the n-term test. So let's look at the integral test. You see all terms are positive. That's good. And the second step is to look at this integration, right? And please recall that, basically speaking, I will drop the formality of the language. I will directly use 1 to infinity for the antiderivative inside. You see, this term is basically the same as x to the power minus 2. So antiderivative, you can use a power rule to resolve this. So it becomes x to the power minus 1 divided by minus 1. So this term is essentially minus 1 over x from 1 to infinity. You see, I'm dropping the limit language. I'm trying to be informal here. So basically, you're having something like that. I replace x by 1 for the lower limit, the second term, right? And for the first term, you can informally think of it as minus 1 over infinity. And this term, of course, conceptually is 0 for 1 over infinity, right? So it means this integral gives you 0 plus 1, which is 1. And 1, of course, is a fixed number. It means that it is a convergent integral, right? And it essentially means that our current problem, which is the infinite series of 1 over n squared, is actually convergent, based on the fact that the corresponding integral we do gives you the convergent integral. And that's the answer to this problem. And I would like to give you a note in the next page about this kind of infinite series. So for this video up to now, we have done two particular examples by the use of the integral test. You see these two type of infinite series, they look quite the same, but the answer is different, right? And the answer is different because by integration, we get different answer. The first one will give you a divergent integral for the function 1 over x, integration from 1 to infinity. And the second one is the integration for 1 over x squared from infinity. You'll get a convergent integral. And you may be wondering about the infinite series of this one, and this one where the p is actually a fixed power. So let's talk about this case. This case, you see, this case is basically meaning the power is 1, p is 1. This case means p is 2, right? And the fact is that all of this infinite series, we can determine whether it is convergent based on the use of the improper integral of this from 1 to infinity. And we'll try to skip the calculation here, but the fact is that whenever p is bigger than 1, it's a convergent integral. And the fact is that for the remaining values of p, like when p is 1 or less, it is actually a divergent integral. And it requires you to work out the integral yourself. I'm not going to do it. But just to let you know, based on the integral test, we get a nice criterion for whatever happening for the infinite series. And it means we can give it as a p-series test for the infinite series. Let me write it down here. Please look at whatever I've written down here. You can call it a p-series test in this case. It occurs to the infinite series where the individual term inside is 1 over n to a fixed power p. And now to judge whether it is convergent, it all depends on the power. If the power itself is bigger than 1, we understand that it is convergent. And take a look at the second example we have done today, right, by the integral test. We have done this case where p is 2, which belongs to this case, and we understand now by the p series it must be convergent. And similarly, for the remaining values, p is 1 or less, like the first case we have done before, we understand that it's a divergent integral. And let's look at some examples now. So please look at the current problem. Is it convergent or divergent? I believe you can do it quite quickly because the bottom, you have to multiply one copy of n to half a copy of n. So altogether, the exponent is 3 over 2, right? It's kind of like n to the power 1.5. And based on the use of the p-test, we can see it because we can pull out the constant 4 as a common factor for all the terms. So the individual term becomes 1 over n to the power 3 over 2. And in general, when you have a common factor for each term inside the infinite series, it really doesn't change the behavior of the infinite series anyway. So now by the p-series test, we can solve it quick because now the p is 3 over 2, which is bigger than 1. Based on the criterion for the p-series test, we understand that this series is actually convergent because now the p is bigger than 1. And let's look at one more problem. So please look at the current problem now. Because the n actually takes a negative power for both terms, I think the nicer way to write it is for the first term, it becomes 1 over n to the power 0.3. For the second term, it becomes 2 over n to the power 1.7. And because there are two terms inside, we can actually split the infinite series into a sum of two infinite series, right? And now is that the first one, based on the p-series test, it is actually divergent because the p is 0.3, which is less than 1. However, for the second one, we can forget about the constant at the top. It doesn't change the behavior of the series. And the p is 1.7, which is bigger than 1. We understand it is convergent, right? Now, please pause a little bit and think about the whole problem. Basically, now our series is the same as something like a divergent series plus another series, which is a convergent series. And are you able to tell me the answer in this case? You see this case when all terms are positive and you get a divergent series. It essentially means conceptually it is an infinity case. When n goes to infinity here, we expect that the sum we go to infinity plus another convergent series. Convergent series basically means it's converging to a fixed value when you keep adding the terms. So basically, it means that when you keep adding so many terms, that's what we expect to see. And it basically means the whole thing as a sum. It still goes to infinity, right? And because it goes to infinity, it means that our series is actually divergent. So I hope you agree with me. It's actually divergent. And we'll do a last problem to the integral test and the p-test. So please look at the current problem. You're given such a series. So whether it is convergent or not depends on your judgment on the infinite series. You see now, in this case, it is not a p-series. It is definitely not a p-series. They are not of the same type. And also, it is not geometric. There's no chance it can be geometric when you have the ln of n term. And I think if you use the n term test, it's not going to work out because of the fact that if you take the limit of all these terms, it's actually like 1 over infinity, which is conceptually the same as 0. Whenever the limit of this term is 0, we say that there's no conclusion by the n-term test. So all these tests don't work. So let's try an integral now. But now you have to do an integral starting from the point 2. So you have to integrate function 1 over x times ln of x, right? And let's think about how to do this integral. I think we can actually use a substitution u equals ln x. So because when you look at the indefinite integral like this here, when I replace u by ln x, I think du is actually 1 over x times dx. You see, the fact is that I can replace this one by u and the remaining term here. It's going to be 1 over x times dx. Coincidentally, it fits into our picture because the whole thing is absorbed by du, which means by the u substitution, now it becomes 1 over u for this term, and the remaining terms are just the same as du. So I'm just doing that. It means the answer is ln u plus c. It means because u is actually ln x, it means it's the same as ln of ln x plus c, right? And let's come back to this integral. And let's do it together. So basically, I'm just writing all the steps down. The second term doesn't matter because the second term is the same as ln of ln 2, which is a constant itself. But the first term conceptually matters a lot. So can you try to understand what happens to this term ln of infinity informally speaking? Ln of infinity, we understood it already earlier in this video that ln of infinity itself is infinity. And it means the whole thing is conceptually like ln of infinity again, which is of course infinity, as we have talked about it already when x goes to infinity for the function ln of x, right? So it means that because of course this one is a constant term, altogether you're getting infinity minus the constant, which is conceptually still an infinity concept, which means it is a divergent integral. So by the integral test, we obtain the answer. I write it down here. So the original series we look at is actually divergent based on an integral test. And that's the end of this video.